Hi folks, and welcome to another episode of Open Analysis Live. So this is the first video that we're going to be putting out on our new YouTube channel, and I just want to say thank you guys so much for all the subscriptions. Make sure to comment below if you have ideas for videos that you want to see us do. We're always looking for new ideas and things like tutorials that you guys might want to see us do. Or if you have interesting malware samples that you want to see us just unpack or do some analysis of, definitely send those our way. So send comments below. Now that we're on YouTube, it should be a lot easier for you guys to actually interact with us. I know when we were on Vimeo, it's kind of hard to set up a Vimeo account. Most people don't have them. And pretty much all the interaction we had was coming through Twitter. And I know that, it's not ideal. You kind of want to just comment on the video. So now you can, we're on YouTube. So today what we're going to do is we're going to talk a little bit about sandboxes and specifically how you can use a sandbox to sort of augment your reverse engineering, or how you can use it to help you sort of zero in on what you want to look at in a binary when you open it in a disassembler. And sort of to do that, we're going to do this in sort of three stages. So first, we're going to do an overview of what sandboxes are and how they work. It's probably going to be a review for most of you, but we'll just do it just to make sure that everyone's on the same page. And then we're going to go into a specific example that I built. That's just a simple thing that we can run in the sandbox. And I'll show you some tricks of how to get extra information out of a sandbox, sort of how things work under the hood. And then we're going to open the sample in IDA, and we're going to talk about how to link what you see in the sandbox to what you're seeing in the disassembled code. So the more you understand about what's going on under the hood in the sandbox and where the information comes from that you're seeing, the easier it's going to be to sort of link that back to the disassembled code you see in IDA and sort of zero in on the stuff that you want to look at. And of course, stuff you want to look at might be things like network traffic or crypto algorithms, stuff like that. So it's basically we're talking about how to go from the sandbox view to the disassembler the most efficient way possible. So starting out, we'll talk about what sandboxes actually are. So this is probably a review for most of you guys. And this is something that me and Sean talk about in our workshops. So you guys, anyone who's taken a workshop with us, you'll probably recognize this slide. And the reason why we do it is because everybody uses sandboxes today, right? It's pretty much one of your de facto basic tools if you're going to be reverse engineering or analyzing malware. But a lot of the time, some of the stuff that's going on under the hood isn't as well understood. And the better that you understand it, the easier it's going to be to take full advantage of the sandbox. So let's just talk about the concept behind sandboxes and an overview of what's going on under the hood. So sandboxes are obviously one of the fundamental tools if you're a reverse engineer, if you're analyzing malware. Most of you are probably using these daily. But what I wanted to do here is I want to just go a little bit in depth into what's going on underneath the hood with the sandbox. And hopefully that will help when we talk about linking what you're seeing in the sandbox to what you see in the disassembled code. So the more that you understand about what's going on under the hood in the sandbox, the easier it's going to be to figure out where that information came from in the binary. So obviously, not all sandboxes are made the same, and there's lots of different ways to implement a sandbox. But what we're looking at here in the slide here about sandbox magic is sort of the way I like to think about sandboxes in a way that gets right down to the core of what makes them so good, what makes them so magic. So there's lots of extra stuff that's going on, especially with some of the modern sandboxes that are coming out. Very interesting stuff going on there. But the core concept of what they're doing and why they're so awesome because of this core concept is kind of what I'm trying to cover here in the slide. So back in like the early 2000s when Packers became super, super popular, or at least when I kind of became aware of how popular they were, the reason for it is because if you packed your binary and you encrypted it, it made it difficult to analyze it because you only had, if you were an analyst, you really could only debug stuff or you could disassemble it and look at the code and try and do it statically. But when people were debugging stuff, one of the neat tricks to do was to look at just the API calls. So whenever a running process wants to interact with the Windows OS, it needs to go through a set of standard APIs, a set of standard functions called the Win32 APIs. And this is basically how a process interacts with any resource on the OS. So if they want to create files, if they want to do any network traffic, basically anything that a process needs to do on the OS or wants to do, they have to go through this set of APIs. And so these APIs are things that we might know of as kernel 32 DLL, ntdll.dll. Anyway, so you had to go through APIs if you want to do anything on the Windows OS. So basically, one of the debugging methods that reverse engineers used to use, and still use today, is to just monitor those APIs to see what the binary is doing. And that way you didn't really have to worry about sort of stepping through and unpacking stuff, because if the binary was running and it wanted to accomplish something on the system, it would have to go through these APIs, right? So it's kind of like malware can hide, but it has to run, that sort of old adage that we hear. So basically, it's the same thing. Like, malware can hide, but it has to do something, right? And if it doesn't want to interact with the OS, then there's no problem, right? It's not malware. So anytime it wants to do any of these things, so network, file system, registry, anything like that, it needs to go through these APIs. So what a sandbox does, it basically packaged up this API monitoring into one container that you could use called a sandbox. And that's really that's the beauty of what a sandbox is. What it does is it just runs the binary, monitors all of the API call traffic, and then reports that API call traffic to the reverse engineer. That's basically what it does. Now, there's lots of like fancy tricks and stuff about how it does this, and this is very much a high level overview. But under the hood, that's all it's doing. So sometimes if you're just debugging something and you want to basically trace some APIs, you can do like your own mini sandbox where you set a bunch of hooks on some of the APIs. You just let the binary run, and then you pull in the results from the different hooks, right? It's something you can do if you're debugging. You create your own like mini sandbox. In fact, one of the things, you guys should let us know in the comments below if you want to see this. One of the things I was thinking about that might be kind of interesting is if we had a small like workshop type thing where we had you guys build your own sandbox. And really what it would be like just a small tool that would hook a bunch of APIs, and then you could run malware in a VM with this tool, and it would print out all the different calls to the APIs, all the data that was sent to these APIs. So let me know if you think that would be an interesting workshop. I think it would be kind of cool. It's something that like I did when I was first learning how to reverse engineer stuff. I think it's kind of like a rite of passage for most reverse engineers to try and write their own like API hooking tool. So let me know in the comments below if this is something that you'd be interested in, and maybe me and Sean can put that together at some point. So basically, this is basically what we have for a sandbox. We have something where the binary is running. We don't really know much about what's going on with the binary, and we don't care, right? We're not looking at the code for the binary. All we're doing is monitoring those calls over to the APIs, and then we're reporting on what data was sent to the APIs, right? That's basically Sandbox 101. So how do they do that? Now, like I said, I'm not going to go too in depth into the mechanics behind all the different ways to implement this. What I will do is kind of give you a brief overview of how Cuckoo works, which is an open source sandbox. Link in the description below. There's also an online version of Cuckoo called malware.com. Unfortunately, it's down right now, and I think they're doing some upgrades or something. So for this video, we're going to be using Hybrid Analysis, which is another online sandbox. And I believe Hybrid Analysis is a userland sandbox. And all that means is that the monitoring that they do, the API monitoring, is done using a DLL in userland rather than using a driver in the kernel. And I, in fact, have a nice little diagram to show you guys what this means. So basically, when you have a sandbox like Cuckoo, this is kind of what it's doing. So we have a couple malware processes here running, and inside each process, the controller will inject a monitor DLL. So it's a custom DLL that's written for Cuckoo or for the sandbox. And that monitor DLL will insert hooks for a bunch of different APIs. So you can see there's a couple hooks in kernel 32 DLL, a couple hooks in ntdll.dll. And again, this is just an example. Like this is really high level stuff. We're not going into detail. But basically, whenever the malware process calls into one of these APIs, instead of calling into the API, it's actually redirected into the monitor DLL, where they record the arguments that are passed to the function or to the API, and then they return control back into the API so that the process can continue. So basically, all it's doing is it's just spying on all those different calls to the APIs and then porting it back to the monitor process. And all of this lives in userland. So there's no kernel drivers or anything like that. It's all just processes running in userland and DLLs that are injected into the process, the malware process. So if you look at this, you can see why userland sandboxes can be detected so easily and they can be circumvented. So obviously the DLL for the sandbox is injected into the process space of the malware, so the malware has full access to it. The hooks are in userland, so these means that there's actually code injected into these DLLs, like kernel32 DLL, ntdll.dll. There's actually code injected into them in order to create that hook to call back into monitor DLL. All of that can be detected. Now, there's a lot of like anti-detection stuff that's also being done that we won't go into detail in. So this is basically like userland sandbox in a nutshell. This is like an overview, nice high level overview of how it works. The only thing that I'm not showing you guys here is how the monitor DLL is actually injected into these processes. Because of course, for each new process that's spawned by the malware, this DLL needs to be injected into it. So there's another portion to this where the controller and the DLL sort of combine to find when new processes are created and they inject the DLL. But that's not really important for what we're talking about today. So basically that new process creation where they're injecting DLLs, the monitor DLL into it, and the hooks where the API calls in the process are being directed up to the monitor DLL, those two things combined is basically what a sandbox is. And all the rest of it, all the lipstick and rouge is just the reporting. So each time one of these APIs is called, there's a bunch of arguments passed to it, and all of the post-processing stuff that's done by a sandbox where they actually show you the results. So they tell you this file was created or this registry key was created. All they're doing is looking at the API calls, and then they're adding some extra information to make it look pretty for you, basically. So that's kind of what I want to drill into today, is talking about underneath the hood when you look at the API calls themselves, because that information is available in the sandbox. What extra information might be available there to help you reverse engineer a sample? Okay, so now that we have an overview of what sandboxes are and how they work underneath the hood, let's jump over to our VM here, and we'll talk about a little sample that I've set up here to demonstrate how this works. So basically what I've done is I have a little bit of C code here. I'll put the source in the description below. I'll put a link to it so you guys can look at it and play along with it at home. I'll also put links to the binary, the compiled binary, in case you guys want to basically do a walkthrough, the same thing that I'm doing in the video. So basically what we have here is we have a small C program where we are creating a file where basically we're finding out where the temp directory is, so we're getting the environment variable temp. We are then creating a file path to the temp directory with a file named test.txt, and then we're sending that over to create file, and we're just creating the file test.txt in temp. That's all we're doing with this. Now there's a bunch of extra boilerplate around here in terms of like how to actually set up that file path. I put in some little statements here saying it worked or it didn't work, just some extra debug type stuff. But basically that's all it does. And what we're going to do is we're going to upload this to Sandbox and take a look at the API calls that come out of it. So with the magic of video, we should have already uploaded this and it'll be available in the Sandbox now. And there we go. So we've uploaded it to hybrid analysis here. So sandbox-test.exe is what it's called. And we can see it doesn't really do anything. All it does is just creates that one file. So there isn't too much to see here. Let's drill into the process specific stuff in hybrid analysis. So to do that, we have to click on the sample, and then we get this nice little view here. And if we look at files, we can see that we've created file test.txt in temp, right? So this is all stuff that you're probably familiar with. It's probably all just review of like what's going on in a sandbox. But what I really want to talk about is this API calls thing over here. So API calls is exactly like what I was describing earlier. These are all the calls, all the arguments that are passed into these API calls that are being monitored by the sandbox. Now, hybrid analysis hides some of these calls. I mean, it's not ideal. It is an free online sandbox. If you set up Cuckoo locally, you have a lot more control over what you see here. But basically, this will do for now. This will do for today. So we can look here. Here's the actual, so the first part here is the API name, so the function name that's called. This is the DLL that it belongs to. And so if we scroll down a little bit, we'll probably see a create file. We see a create file here, and it's nt create file in ntdll.dll, and the file name here is in the temp file, and it's test.txt, right? So by looking at these API calls, we can gain the same information that we would have seen nicely presented to you guys in the Files tab here. So here it's all nicely presented, but really the raw data exists here in the API calls. So what I want to do is I want to talk a little bit about the same thing that I talk about in basically all my videos, which is the API call chain in the Windows 32 API. So this is basically the function that you call in your code is not the same function that is hooked by Sandbox. So basically the function that you're calling in your code is not the same function that you're seeing here. So you're not in our code, we were calling create file. Here we see nt create file in ntdll.dll. It's very rare that you would call an nt call from your code, right? You're usually calling a little bit higher up. And so what I've done is I've made a nice little diagram to explain how this all works. So here's basically the call chain that happens. So here's our code. We called create file w, which is a function or an API in kernel 32 DLL. And then kernel 32 DLL internally called nt create file in ntdll.dll, right? So that's one trick that's important to remember when you're looking at the API calls in a sandbox. They will probably be lower in the call chain than the stuff that actually exists in your code. And the reason for this is because there are a bunch of different calls that may call nt create file, because nt create file is the lowest userland call before you get into the kernel. So if you hook this, you'll grab all the create file calls. Whereas if you hook higher up, you may have to hook a bunch of different stuff. So it's basically just more efficient to hook lower. And there's one thing I want to point out, because when we get into looking at the actual source code and going through the debugger, this is going to be important. So here's the create file arguments, what's pushed on the stack here. The first thing pushed on the stack, the first argument, is going to be a pointer to a C string, which is the file name, right? So the first argument is a pointer to the file name that you want to create. It's the file, or a file path, I guess, to the file that you want to create. So this would be the temp directory / test.txt. However, when it gets transformed into an nt create file call, you can see that the arguments are a little bit different, and there's no file name being passed to nt create file. Instead, there's this object here called object attributes. And so what we need to do is we need to take a closer look at what object attributes actually is. Here we go. So here we can look at, here's nt create file, and there's that object attributes. Here's the definition for object attributes. And you can see here the second parameter here, the second argument, is something called object name. And object name is a pointer to a Unicode string. And remember, Unicode strings aren't just buffers of text. They actually have their own struct where there's a bunch of extra information. So the first short is going to be the length. The second short is the max length. And then the third argument here is actually the pointer to the buffer that contains the string. So what this all means is if we're looking at the call to nt create file, we need to first look for the pointer to the object attributes, which is going to be the third thing on the stack. And then we need to go down, we need to go one D word down further to find the second argument, or the second parameter in the struct here. Which is going to be a pointer to a Unicode string, and then we need to go one short, two shorts down to find the actual the buffer pointer. So it's not just going to be a nice string that you see on the stack. It's going to be this long chain of stuff, and you'll see that in a minute when we pop into the debugger and show you. So what we can do here, now that we understand that, we can pop over to our IDA instance here. Let's go back and we'll open this sandbox test.exe in IDA, and you can see it's already open here. I put it into source code view with our disassembler, or sorry, our decompiler, the Hexphrase decompiler, so we can see it looks fairly similar to our original source code here, right? So here's our create file. There's a bunch of stuff with the file name and the file path at the top. So here's our create file, and here's a bunch of stuff. Looks like the get m for the temp, and then some stuff going on with the return value. These are just basically converting from string into wide string, then from wide string into wide C string, because that's what needs to be passed to create file W. So here it's pretty simple. We just looked at the code, and we can see this create file API call immediately, and so we can match that up to the create file call that exists in our sandbox here. But here's the trick. So remember I said NT create file is further down the call chain than what we have in our code here. Here we have create file. So what would you do if you wanted to actually find that NT create file call? This becomes important if this binary was packed and you couldn't easily read the code. So let's say you were looking at a packed binary and you wanted to find that NT call. Well, you know that there's a call being made to NT create file. So what you can do is you can open up your file in IDA, disassemble it. So we'll go to our disassembly here. And so again, imagine that this call to create file is not apparent. Imagine that this is a packed binary, so you can't see that. The easiest way to locate that, so the easiest way to map what's in the binary to what you saw in the sandbox, is to actually hook the same API call in with a debugger and run the binary until you get to that API call and then walk backwards. And the advantage of this is that then if you see something interesting in the sandbox, like let's say that file is, maybe it's a configuration file or something like that, and you want to see how it's built, or maybe it's encrypted and you want to find the encryption algorithm. The trick here is you see that in the sandbox, so you see that file name is being created, and you see that it's using NT create file. So then you go to your binary, you open it in a debugger, you put a breakpoint on that same API, so that NT create file, you run until you hit the breakpoint, and then you step back into the source code, the original source code here, so you can see where in the binary that was called from. And then you know the location in the binary that you want to focus your analysis on. So this is the main trick. This is the whole crux of this video, is basically how to link from interesting stuff in the sandbox to what's in the binary, and how to sort of put that link together. And the easiest way to do that is with a debugger and a breakpoint. So let's get that rolling here. We're going to use, because this is just a sample file that I built myself, it's benign, we're going to use a local debugger. So I'll just use a local Windows debugger. And what I like to do usually is I like to put a breakpoint on the beginning on the main function here. So this is when main. And I like to put a breakpoint there because I like to run the binary until we get to the main. And then I set my breakpoint on the API call that I want to stop on, because I don't want it to be called before I enter the binary that I'm analyzing. So some of the setup for the binary, maybe when they're loading other DLLs and stuff like that, maybe like create file is probably not going to be called, but maybe there is an API call like, I don't know, like load DLL or something like that you want to hook that is called by other DLLs or by the process setup. So it's always best to run until and put a breakpoint on the main entry point of the malware that you're analyzing. You stop there, and then you set your breakpoint on the API that you want to run until. And then that way you avoid anything that might be false positives, basically, while the process is starting up. So let's give this a run. We run until we get to the beginning here. And then you guys have probably seen our other videos where we talk about setting up the view here for a debugger in IDA. But if you haven't, there's another video we have on like using IDA to analyze malware. I think it's called like IDA tips or something like that. I'll link it below as well. But it's another video on our channel you might want to check out. So I'm just going to set this up here. I want to go to toolbars advanced. Yes. And then over here in my modules window, I'm going to want to go into ntdll.dll, and here I'm going to do a Control F to search for create file. Here's nt create file, so I just double click to bring it up, and then I can set a breakpoint on the entry of nt create file, and then I just run until I get there. So we've hit this breakpoint, and now I can show you guys, it's going to get a little bit complicated, but I can show you guys this very interesting chain where you can find the actual file name and file path from the call to nt create file. So if we go back here, we are just entered into nt create file, so we know, let's take a closer look at our stack here. So this is the return address. The first argument on the stack here is the return address from where the nt-create file was called. So here we have create file w, which we would have expected. And then the next thing on the stack, so on our stack, we have the first thing is the file handle, then we have desired access, and then the third thing on the stack is this object attributes thing. So we have, this is our return. So 1, 2, 3, third thing on the stack. Did I do that right? 1, 2, no, 3, third thing on the stack. So let's copy that address and G to go to that address, paste it in here. Scroll over so we can see it. So basically, if we look at our diagram here, we are pointing from object attributes. So we point it over here to initialize object attributes, which is basically, there's going to be a size, and then we have the first attribute, and then we have the object name. So let's pop over here and let's turn it into, so first thing we have is our size. That's a D word. And something that we don't care about is our D word. And then we have our pointer to our Unicode string. So now we need to look at the definition of the Unicode string. So let's pop back over here. And so we have the first short is length, the second short is maximum, and then maximum length, and then the third thing is the buffer. So we have 2 shorts, and then we have the pointer to the buffer. Let's see here, we have 1 short, 2 shorts, and then the buffer. So there we go, we found our file path that we're sending to create file. And like I said before, if this was obfuscated code and we use this breakpoint, this hook, to basically find an interesting part in the code, what we could do now is we could return through those calls to get back to our original binary, and we would know the section of the binary that we want to focus our analysis on. Like I said before, for instance, if this was a file that was encrypted, we could look at what functions called that function in the binary, and maybe they were the encryption algorithms or something like that. It's basically just gives us an area to focus on, to focus our reverse engineering. So let's just quickly do that. We'll just step back into the code and then we'll call it a day. The way to do that is we want to jump to our instruction pointer here. So here's the return. We basically just want to run until we return from this function in ntdll.dll. Let's run until we return, and we return into kernel base. So let's run until we return from kernel base into kernel 32. And then I believe if we run until we return, we'll return, yep, back into our main code. So, and you can see we've returned right after the call to create file in our main binary here. So that's basically how you use the sandbox to identify an area of the binary that is interesting. Hopefully that kind of puts all of this together, and you guys can use this to sort of help make your reverse engineering a little bit easier. So hopefully you found that helpful, or at least interesting. Let us know what you thought. Comment below, like, subscribe. I can say that now that we're on YouTube. I should mention also our Twitter bios are linked below, our Twitter handles. Our DMs are open, so if you don't have an account on YouTube, you can always message us there. We're always looking for feedback, stuff that you want to see us improve on, topics that you want to see us cover, questions that you had. Maybe we messed up. I mean, I'm kind of just doing this live, so hopefully if I did make a mistake, let me know. And as always, keep exposing the mechanics behind the malware and stay curious.